very happy to have Professor James Taylor visiting us today from the University of Waterloo. James was here in the early 90s and then did his PhD at the University of Victoria. He's an expert on several aspects of dark matter halos, including their clustering, gravitational lensing, and his research combines observations, simulations, and analytical theory. Today, he's going to talk about the density of dark matter halos. How much do we understand? Thank you.
Okay, well, thank you very much for inviting me. I'm glad to see it's an audience at business with various members of the audience, too. So it's always good to combine those things. Yeah, this is a bit of a, trip down memory lane, because I used to, amongst other things, I used to organize the coffee. Back when part of this was the astronomy department, I used to organize the coffee many, many years ago, sometime in the early mid-90s. So things seem oddly familiar. So I was going to talk about what happens in dark matter halos on those sort of small scales in the middles of dark matter halos. This is work done with a large number of people through several different projects. In particular, I'll highlight the work of a recent graduate, Nicole Drakos. Let me just see if I'm getting this working. Well, oh, there we go. Yeah, if not, I may just use the stick. Who's is now at a postdoc in Santa Cruz, but I'll show a lot of her work. And then also another former PhD student, Chiamaka Okoli, who was at the University of Waterloo, along with Nyaya Shorty. We're all part of this fairly new Center for Astrophysics that started there, so you're all welcome to come and visit. We don't actually have a building or anywhere to sit or anything like that, but it's a sort of virtual thing. So we'll take you to Tim Hortons for coffee or that kind of thing. And we have grand plans. So anyway. And then let's see. So with Nicole, I did some work also with Andrew Benson on some of this. And then more recently, a year or two ago, I got kind of, well, not dragged. I mean, I was happy to get involved in this, but I got involved with observers, in particular Stéphane Courteau and Nathalie Ouellette, on a sort of galaxy side of what I'll talk about. And then some of Nicole's work we also did with people at ICRAR in Australia, Aaron Robotham and Chris Powers. So I think it's clear that cold dark matter, CDM, is here to stay. This comes up from time to time because I sometimes give talks to physicists who are not astronomers or astrophysicists, and I realize how confused. If you have 3 or 4 or 5 sigma evidence for something, it's easy to talk about how much evidence there is and what would happen if it didn't exist and so on. It's quite hard with dark matter. I have no idea, but my guess is, we have 5,000 sigma evidence for dark matter. In the sense that there are all these basic pillars of cosmology, the CMB, large-scale structure, BAO, cluster number counts, the properties of individual clusters, other things that didn't fit on the screen, like cosmic shear statistics and so on. All these things are based on models which rely on dark matter being there. And if you wanted to take that back out, you would have to go and construct by hand models to match all of this stuff. And I think what you'd wind up with empirically is something that acts exactly like cold dark matter, except on 1 or 2 scales. Right? So you could just say whatever is doing this, even if it's a combination of strange scalar fields or more than one particle or whatever the explanation is fundamentally, that's what you mean by cold dark matter, right? And the one thing you might worry about is, is it really cold? And is it really, what is it? So although the observations are all sort of consistent with one simple thing, the theoretical landscape has got increasingly baroque, and a lot of this has been, there's just been a sort of efflorescence of theories in the last 10 or 15 years, as a result of which there is no one good model for dark matter. There are dozens of them, right? And they are actually good models. They do other things, and they're interesting in other ways. It's interesting that none of this fits into the standard model. And the standard model is such that you can't just add pieces to it. It works by symmetries. So if you want to change anything or grow it at all, you actually have to add a new symmetry, which at least, naively doubles it, right? So if you think of that in terms of investment, if we figure out what the dark matter candidate is, and if the world turns out to be run by rational people who care about fundamental physics, which is a big if, you would imagine you might double the number of people working in particle physics. That would be a sensible thing to do if we ever identified what dark matter was, right? That would be a good investment. And there is significant investment, and this is something I actually want to, I always meaning as a little project to go and track down the people who run, for instance, direct detection experiments where you look for dark matter particles in the lab and kind of try to ask them what the budget is, right? So my sense is direct detection, for instance, is a small part of high energy physics, but it's not a totally negligible part. It might be 5 or 10%, and that represents then hundreds of millions of dollars being spent to try to find what dark matter is. Okay. So that's the motivation. The motivation to study halos is, first of all, this sense that they underpin all of structure formation. They're the sort of basic model. They're kind of like the Bohr atom or something. You want to understand them first. I was checking, because I'm always a bit vague on 21 centimeter Lyman alpha forest and so on. Anyway, I was checking with Hamza, and sure enough, she agrees that most baryons are in halos. Most of the baryons we can never study or know about, right? I mean, lots of baryons are not in halos, but the ones we can study are, for the most part, in halos, even with things like 21 centimeter. So there's that, theoretical motivation to understand things. And then also, if we want to figure out what dark matter is, most of our constraints are constraints derived within halos. So we want to sort of understand those. Of course, we have, we know, I'll show you roughly how halos work. So why isn't that good enough? So there are a couple of complications in this. The first is that halo formation is nonlinear, so you have to do numerical simulations. There's no simple analytic way of predicting what you're going to see, unlike things like, say, the CMB. And the simplest example of that is the most basic thing we know about dark matter halos. Their density profile was never successfully predicted until simulations came along. There were steps towards anticipating what that would look like, but the big triumph of numerical work was really to find that there is this density profile whose origin we still don't totally understand. We don't have any direct observational probes. We're always inferring how dark matter is distributed or behaves from more or less indirect reconstructions through lensing or through dynamics. There are some important quantities, I'll talk later on about the boost factor, that require us to actually know how dark matter clusters and behaves on all scales of interest. And the scales of interest go down to sort of planet masses. So they're about 20 decades in mass that we need to cover. That means we're forced to first run simulations, because it's a nonlinear problem, but then also extrapolate from them, and extrapolate enormously over a very wide range. So there's really quite a pressure to have a theory you really believe and you think is fundamental in explaining how these things work. And then observationally, I also just wanted to show you, in some of the stuff I'll talk about with galaxies, unfortunately, we really don't have anywhere near the baseline we would like to study the matter distribution in galaxies. We have a lot of information about galaxies, and it all lives down here on the sort of 10 kiloparsec scale. For the Milky Way, the virial radius is probably out somewhere at 250 or 300 kpc. And the place where you'd really like to do a lot of tests is actually around here. It's out at around 50. Right? And you could just see there's nothing there, right? There's nothing to look at, unless you want to go and look at something really strange and esoteric, like globular clusters. Now, some people believe globular clusters are real. Anyway, sorry. Yes?
So what's special about them to succeed with
Oh, this is the scale radius, and actually I'll show you in a slide or two why I care about that. But that's an interesting, if I want to know stuff about the halo, that's the scale I want to measure on. Conversely, the fact they're there's something detectable here, would make me worry baryons have modified what's going on here in complicated ways, right? So it's also partly just to get away from the baryons and have, it's this sort of, you're caught between two things. You want to probe the distribution where you still have things that can measure it, but where the baryons haven't had a significant effect. Okay, so I'm going to review a few things about halos, in particular this point about the scale radius. And then I was going to talk about three things. The first was how halos behave in mergers. And that's partly because, well, we did a lot of work on that recently. But it's partly also because it sort of motivated a different approach in my mind to understanding or modeling halos that I'll talk about a bit, which is essentially just looking at them through their distribution functions and really thinking about the distribution function. And then I'll point out connections, two observational connections, one to dark matter detection, here really mainly indirect detection, and one to galaxy dynamics. Okay. So on large scales, structure forms a variety of things, sheets, filaments, and eventually halos. Probably the best way to show this is just with a movie. Is this playing? Yeah, so here's a movie. This is from Thomas Bell's group. And it's nice because the combination of resolution and mass scale is such that you see these very fine filaments in this particular visualization. So the matter collapses into sheets. The sheets drain into filaments. The filaments drain into sort of regions in the center. And you can see that those are very chaotic places. The main discovery about them was this discovery from, what is that, 20 odd years ago now, 25 years ago, that if you average over the knot that sits at the intersection of the filaments, the distribution of matter there is sort of universal. It's independent of the details of the cosmology, it's independent of the mass, it's independent of redshift. You can always fit it with the same form. And that form is a broken power law that has one slope in the outer bit about -3, one slope in the inner bit about -1, and that breaks between them. And you can define the radius at which it's -2. So it's transitioning between these, the scale radius, right? And I'll talk about the concentration parameter, which is just how big the system is, where its virial radius is in units of the scale radius. That number is 3 or 4 typically for galaxy clusters, and it's 10 or 12 for galaxies. And it might in principle be higher for even smaller objects like 20 or 30. So this is a static picture. It's supposed to be valid at all times for all objects in an average sense. You can see that there's noise in the outer parts. So halos are forming and digesting things, and that material's not in equilibrium in the outer parts, and therefore the density profiles are not smooth in this case. This was also shockingly low resolution where this was discovered. So these have a few tens of thousands of particles each. I think the main evolutionary understanding that's come out of, let's say, the last 10 or 15 years of work on this is what the concentration means. The concentration is basically an age indicator. And this was already there. The idea of this was already there in the original NFW papers. It's just, I think it's been fleshed out a lot more. That a system forms. It's having to do that by bringing in material and counteracting expansion. And therefore it forms with a density that is some multiple of the background density at the time it forms. And then it just sits there and it sort of nucleates the growth of material around it. As the universe expands, material around it winds up getting incorporated. So you have a sort of what I would call a core and then an envelope. And the only problem with that is, for some reason in the field, the people who do galaxy rotation curves have this convention that core means constant density, which, as far as I know, if you look up core in the dictionary, it doesn't mean constant density. But anyway, so they don't always like calling this a core, so you could call it a nucleus or something.
So it's basically representing the last major merger?
Yeah, exactly. Exactly. So it's the last major merger, or more broadly, I'll show a picture later on, it's the end of the era of rapid growth. So you might have multiple major mergers or something going on. But there's some period when things are building up, all this is being stirred up, and it produces some kind of thing. And that thing always has a concentration of 3 or 4. And then it sits there, and it's like, you know, a rock appearing as the tide goes out, that it just sits there and the tide goes out. And in fact, a lot of the growth has been shown to be artificial in the sense that the density is not actually changing at all. It's just our threshold for where we define the virial radius goes down, right? So the nice thing about this is it means there's a mapping between the mass distribution and the history of these things. And of course, history is something that's not directly observable. So this potentially is, you know, this very interesting property of halos, that they tell you something about the history of that patch. Yeah, exactly. You could go to, so the splashback radius would kind of be out at, you know, sort of 1.7-ish, something like that. Yeah, and you could do the same thing.
Depend on the background density.
So there is this issue with the virial radius that it's not a great radius to use, because what do you really mean, right? Yeah. But this general pattern that this bit forms early is, and they're also, I mean, the NFW model of this is a little bit different from what I'm saying. Their model is that you assemble material to some density, but not necessarily in one object. So their model is based on how much mass is in this bit versus what actual size it has. And I think the details of, you know, exactly how this works are not totally, you know, between the variants of the models, they're not totally worked out.
Does the mass go up between none and gold?
Here, I guess I sized them so they have the same total mass at redshift 0, let's say. But the density would be a lot higher in the old one. So, so much of the mass is in the outer bit, it doesn't make much difference to the density in the outer region. But then the density keeps rising to, sorry, I've done my color scheme is wrong here. That's, okay, I need to go do that. If you just imagine this plot, that this is blue and that's red, that would, there we go. That would make a lot more sense. It's funny, you don't notice these things until you read over them in detail. But, so I think the other thing just to be, you know, conscious of is that halos grow through mergers. That's not something we have completely seen happen, but it's pretty clear it has to happen. For instance, on cluster scales, we know that must happen down to galaxy scales because we know how much power there is empirically on galaxy scales. Below galaxy scales, this remains a theoretical prediction. It's not proven that this is the case. And the mergers, if they happen, are inefficient. Basically, there's such a huge density contrast within a single object that the core of it is very dense. And when the whole thing falls in, the outskirts get tidally stripped off, but the core survives. And you see this in n-body simulations, that you keep the remains of pretty much everything that merged, right? So you get thousands of objects. This is also interesting if you're looking at observational constraints, because most galaxies, I mean, the famous statement that I've sort of tried to track down, is a little hard to track down, is most galaxies live in groups. You probably all heard that. So everyone heard that most galaxies live in groups. So it's hard to actually track down that reference that says that. But by implication, most galaxies live in subhalos, not independent halos. And therefore, actually, for instance, tidal stripping is actually relevant to pretty much all the galaxies we see. At some level, not the Milky Way maybe, but you know, the average galaxy out there has been in a tidally stripped halo. Let me just show you this. Here is another. This is a great movie just to show you what a messy dynamical situation this is. So I have my early linear fluctuations. They eventually collapse and start forming things I can't see because the resolution of the movie's low, because I didn't want to download too big a file. But you start forming things along the filaments, and the filaments are coming together in a sort of knot that'll be forming here. This is all rotating around, which is why the stuff in the foreground keeps passing by. And eventually, if you watch, you'll see things kind of drain down the filament into a central node, where a big halo is going to form. And as it forms, if you look closely here, you'll see the cores of previously formed halos merging, and they're actually leaving behind a lot of debris. So there's a lot of tidal stripping going on, but there's a lot of mess left over. And this will keep on running, and you'll wind up with something at redshift 0 that has an enormous amount of dense substructure in it. Let's see, it's almost finished, I think. Anyway, you can see all the subhalos in it. If you're a simulator and you've done this, you'll also notice it's actually over-merged here. There's artificial numerical disruption in the middle of this, so you see more of the substructure in the outer parts. So that's a technical problem. We don't actually know always exactly how much substructure survives. And the thing about this is if you go and match this to a galaxy cluster, well, galaxy clusters have lots of galaxies in them. So you can imagine putting a galaxy in each lump, and that seems okay. But if you imagine this being the Milky Way, this is horrifying, right? Because there's stuff all over the place. And what is there, to trace all that structure? Okay. Sorry, how's this doing for... Oh, it's got quite a ways to go. I think I'll stop it there. You get the idea. Anyway, so that's the picture to sort of have in your head when I'm talking about halos and halo structure. Okay. I said I want to extrapolate over 10 decades at least in mass from those simulations down to very small scales. And I want to do it in a way I can believe. So I want some theory behind this, not just simulations. I want to try to understand what's going on when halos merge and when they form. And before you even start that, you have to decide what's your broad strategy going to be. So after thinking about mass loss, the decision was that the strategy is going to be to think about this in terms of a distribution function. To imagine that I'm describing an isolated self-gravitating system that has a well-defined distribution function. And to ask how that builds up as the system grows and how that changes as the system merges or gets stripped. So specifically, can I use a model like that to describe tidal mass loss? And if I do that, then what does it imply for the density right at the center of the halo, which is the place where I care about it? And then finally, can I sort of constrain that observationally? Okay. So all of this is going to hinge on a theory that was developed a long, long time ago for star clusters. So it's sort of old school, vintage stuff. And this is theory that was developed to understand star clusters by Ivan King, amongst others. And this is called lowering, when you lower the distribution function. So let me back up a little bit and just sort of introduce, why you want a distribution function and how that works technically. This is kind of fun. This is something I now teach because I teach a computational physics course, and it's a nice thing to tell people, I want to set up a ball of self-gravitating particles and have that be stable, have the structure be stable. How do I do that, right? So I show them, they're an undergrad class, so I show them the first part of the trick, which is how I set up a density profile, right, just statically. But I don't talk about the second profile, so you all know the trick here that you integrate over the mass distribution and you get some monotonic cumulative thing, and then you can just pick mass fractions uniformly and map them onto radius, right? But how do you pick velocities so that when you start the thing off, it runs, and it doesn't immediately change its own density profile, right? So there, the bit of theory that helps you is this trick expressed through the Jeans theorems, that if you find things that are conserved by the orbit and pick in terms of those conserved quantities, integrals of motion, then you'll actually guarantee to satisfy the dynamical sort of stability criteria for the thing, the Jeans equations. So this is usually done in terms of this confusing quantity. It's confusing because there's a minus sign in here. The convention long ago was chosen that this should be a positive quantity. So you take the energy, you give it some baseline offset, and you take minus that. And what is it you have? Well, you have this quantity that gets super confusing every time you're getting into the calculations. So I started giving it a different and very awkward name deliberately so that I would not I wouldn't remember the awkward definition or construction of this quantity. It would sort of remain present. So I call this the bindedness. So this is the bindedness. It's like binding energy, except if you just said binding energy, you might forget the minus sign, right? Anyway. So the bindedness, the idea is things in the middle are very binded, or bound, I guess. And things at the outskirts, as you get further and further away, your bindedness goes to 0, right? Okay. So given bindedness, then I can say the density at any one point is an integral over the various possible values of the bindedness at that radius. And this equation, it turns out I can then invert. And the inversion tells me how to construct the distribution function. So how do I pick how many things have a given bindedness? And the bindedness in turn through the energy tells me if I'm at a given position and I know the density profile and the potential, it tells me what velocity to pick. So this basically tells me an energy and therefore a velocity to pick for a particle. Yeah?
So you say stable, what exactly do you mean?
Sorry, when I say
stable, you want the system to be stable.
What I want is the averaged, the density profile smoothed over the particles. I mean, I'm always realizing this with a finite number of particles. So in that sense, it's never 100%, long-term stable. But I want short-term, in the short term, I don't want the density profile to change. And once I get into the distribution function, I don't want that to change either. So I want that to look the same average in the limit where I'm averaging over a number of particles. Yeah. And we have code that sets this up, and sure enough, it's very, very stable, right? It's not stable out to infinity because, of course, I have individual particles, and eventually the system will relax, and two-body effects will break it all up. So forms, analytic forms or fits to this for instance, NFW profiles are not that old. They're fairly, it took a while to sort of develop this, but anyway, Larry Widrow, for instance, published an analytic one for the, or did the calculation for the NFW profile. This is his plot. And this is sort of showing you what fraction of things have a certain amount of bindedness. And bindedness is 0 at the outer edge of the system, and then here's the cusp. And this is just comparing it to various other similar models and density profiles. Okay, so that's just for a infinitely extended isolated system. Then the idea is if I have a system and I'm going to strip it tidally, I want the number of particles to go to 0 at some finite radius. I want to cut off things that are loosely bound. So I'll have some typical binding energy, and beyond that, I'll want things to go to 0. So I can take my original expression for, let's say, an NFW distribution function and say, okay, how can I modify that so it goes to 0 at some value of the relative energy? And there are different ways of doing that. I could just do this, for instance. I could have a new function, f of script e, which was just the same distribution function, but applied to this shifted variable. Or I could subtract the original function from itself. There are different ways I can imagine constructing something that satisfies this. And we actually tried. We set up these systems with particles with different distribution functions and let them go and looked to see how long did it take them to evolve, so how stable were they. And we found, for instance, that this is actually more stable, slightly more stable than this. So it's interesting. There are subtle differences in how you set this up. And if you set up something like this, what you get is the black curve here is the original NFW profile. And then as you vary your tidal energy, you get things that are cut off, that have stable but finite density profiles that drop to 0 to finite radius. Yeah?
Why do you use the binding energy as the criterion for tunnel stripping? I would imagine the low density would be a better criterion because you always truncated the density where you greater than the average density.
Let me come back. Can I come back to that? Because that's a very deep question. And I think I'm going to get deep in another maybe 5 slides. Yeah, that's an excellent but deep question. Yeah.
Tidal field, of course, always has a particular shape to it, and you're modeling its effect with a
That's part of this deep question, I think. Yeah. The problem is not that these are both valid points, and then you can come up with about 5 other problems like that. And pretty quickly what you realize is, you know, we're stuck. There's no way of solving this analytically. You just have to run an n-body simulation, right? So for instance, particles get stripped off depending on where they are in the phase of their orbit as they go round, right?
Well, if the surface is
Yeah.
going around,
Yeah.
then you're averaging the tidal field.
And things like the circularity of the orbit within the system would make a difference. So I used to worry about that, and in fact we still worry about that in these papers. I'll show you some results on that. Lately I've learned to stop worrying, because what I've realized is we're never going to describe the problem in that level of detail at all. A better way, I think, of thinking about it is to say you want to expand around some baseline, and this is the baseline I think to expand around. And then all those things you introduce as corrections where you say, we know that happens, how big an effect is it, right? But the step of saying I need a spherical cow to begin with, this is sort of the spherical cow beginning. So the spherical cow is basically this. I have a 1-parameter way of stripping structures, right? Yeah. Yeah. Yeah.
Very discussed, but it must have been at some levels that if I tidally strip a spherical star cluster, it has to have some degree of non-sphericity.
Yeah. So it's funny. What I don't have those pictures, unfortunately, but Nicole had that in the latest paper, which I think was submitted with those pictures. So the interesting thing is the material that gets stripped off is very non-spherical. But the stuff that stays behind rearranges itself and becomes quite spherical again. And I think that's actually part of the deep thing is when something gets stripped, it kind of strips, it goes out to apocenter, and it goes back in. One way of understanding which particles get stripped is the particles that get stripped are the particles that interact strongly. And those are the ones that wind up very non-spherical, but they get stripped. So you always wind up with something that's roughly spherical at apocenter, kind of by definition, because if you weren't very spherical, you would have got stripped off. So there's a natural, like the thing kind of tunes itself to get back into something that looks like a spherical, you know, system. Anyway, the appeal to this is all based on you can go back and look at King models with globular clusters in the 60s. It's exactly the same thing. And in fact, there are different papers arguing about, different ways of doing this. The great appeal to King models was if you took King model density profiles and looked at globular clusters, King models look exactly like some globular clusters, like exactly, with all these wiggles and features in them. So it was this sort of dramatic confirmation that you're understanding the problem the right way. Here it's a little less dramatic because we were just using simulations, but this empirically is what things look like when they're stripped. This was work by Eric Hayashi years ago. So empirically, it was known that there's a kind of one-dimensional thing that happens to halos when they get stripped. And you can describe it this way. You can take the original density profile and truncate it with an extra factor in front. This gives you an outer slope that goes as r to the -6, which is very similar to what you see in globulars. And if you put this lowering model on top, it fits pretty much perfectly. You can't really see how well it fits there, but we have, I think I'll show some residuals in one of these. Basically, you do a very, very good job of fitting what happens in the simulations with these lowered models that just have a single free parameter you're varying. And you do well not only in the density profiles, but also in the distribution function, where here it's this bit where you shift and you cut a certain amount off. So here the model is this, and the just the binned distribution function we get in practice looks like this in the background. This is doing, for instance, an attempt at a projection of the full phase space. So this is velocity, total velocity versus radius. And these are the simulation results, and these are the models. So you really get quite good, detailed agreement between how many things are at what velocities. And the interesting thing is these are the residuals, and the residuals are not random. I mean, it's interesting, you see patterns in the residuals, which are, I think, shells of material sloshing in and out, right? So that would be a sort of higher order correction. Okay, so that's nice. That's all with an NFW profile. There are actually several other models for tidally stripped NFW profiles out there, and they do, more or less well. One nice thing about this, though, is you can lower anything. And we've tried lowering other things like Hernquist profiles, Anasto profiles, King models, and so on. And then when you run simulations, you get good agreement to what you see. So it seems like this is a kind of universal way of roughly describing how mass loss works. Why does it work so well? So this is where maybe here I could get philosophical. If you think about it, I was talking originally about an isolated spherical system. The Jeans theorems tell me that my distribution function can only depend on integrals of motion, and if the whole thing is isolated, spherical, and isotropic, that just leaves you with the energy, so the distribution function is just a function of energy. So there you go. And that is not at all the situation we're considering here, because I've got a small thing in a big potential. So there's actually almost no symmetry spatially. There's one axial symmetry running through the small thing and the big thing, and you can use that to generate what's called the Jacobi integral. So if you go and read in Binney and Tremaine, the classic tidal radius is based on that calculation. But even there, that only works in a in a circular orbit where you could go into a co-rotating frame. If you're on a general orbit, you have a time-varying potential. You're stuffed. I mean, there's nothing there. There's nothing to work with theoretically, right? Why does this work? Well, I think it works because of what I was saying about apocenter, that you go out to apocenter and it's kind of like you're isolated, and you go back in and you're not, and you go back out and it's kind of like you're isolated. So really what you want to know is, what's the orbit averaged effect? Can I make a model where I have one distribution function here with an energy epsilon 1? Next time around, I have a different one with an energy epsilon 2, and I have some mapping between those. And I think what we're showing is that mapping is predominantly just adding a constant or subtracting a constant. It's just lowering. I just take a chunk off every time, and the thing loses mass accordingly. So this is a test of that. This is the, yeah.
That means that the distribution function, even for the very bounded particles, is being lowered. So that they, even though you might say, well, they ought to be, like you were talking about in your virialized hail at the beginning, they ought to be sort of impervious to what's going on around them.
So this is why we care. So we care because we want to know what happens at very small radii or high bindedness. And the problem with all the fits to the density profile is that's where they're least accurate, and they don't tell you what's going on with those particles. At what rate are you losing the most bound particles? And that's really what we're trying to get to. Yeah, is exactly that. What happens to the energies of the most bound particles? And are they affected too? This is showing which particles come off in energy space, and you can see it's a narrow slice in energy. This is energy versus, this is relative energy here. This is orbital circularity, so it's like angular momentum. So the fact this is pretty vertical tells you on the whole things are getting taken out in energy space. But what's really interesting about this is these are the things lost. Now I'm going to get this the wrong way around, but it doesn't really matter. I think these are the things lost on, let's say, orbit 1 in units of the energy they had going into that orbit. Okay? But this is the things that are lost in units of the energy they had 2 orbits ago. This is the things that are lost in units of the energy they had 3 orbits ago. Right? So in other words, if I take particles that are lost and ask where were they in the distribution function on previous orbits, I have fairly narrow slices going way back. So it really is like a conveyor belt where, you know, you put your lemmings on the conveyor belt and they just go along and they drop off. And on each orbit, the conveyor belt is going up one step, right? So this was kind of a test of why does this work? And it seems, you know, maybe another less emotionally charged and you know, for the vegans in the audience, you can think about it as an onion or something, right? Like you're taking off layers of the onion at each step. And each step, your onion's going in with one layer less. But everything else is just, I don't know, maybe you're measuring the pressure of the onion or something. Like everything gets lifted up by the same amount. Okay. You can turn this into a full mass loss model. To do that, you would have to say, what is this tidal energy? That, you know, how much are things lowered? And Nicole did that. So she has an estimate of that based on the usual tidal radius calculation. And that does pretty well at matching simulations. I think I'm actually not so interested in this now because what I'm getting interested in is the scatter. So the energies get shifted orbit to orbit. The stuff outside the tidal energy gets taken off, but the energies also get a little bit of scatter orbit to orbit, and I think we can actually do a more accurate match to mass loss by including that scatter. This is just showing what that scatter is, so this is how much the relative energy varies from one orbit to another, and you can see it's given a kind of Gaussian-ish sort of scatter in values from one orbit to another. So if we could model this, I think you could really get these very accurate predictions of how much things lose, yes.
You may just actually answer my question. So you're fitting a lowering rate? You're not predicting the lowering rate?
In this one, we're actually predicting a lowering rate.
Okay.
Basically using, there are a couple of different ways of defining the tidal radius. So we pick one of those, and it turns out that's the only free parameter is what value of the tidal radius you kind of, there's a sort of arbitrary constant in the tidal radius. So fixing that constant, we get all of this, and it matches everything, and it does about as well as the other models. But it doesn't match things perfectly, like the simulations here are the colored points. I mean, here's one where, okay, there was a bit less mass loss in the simulation than you predict on the first orbit. So my theory is we might be able to do even better by including this second order term. The first order term would be the shift in energy on every orbit, and the second one would be the scatter, right? I mean, it's also maybe a bit like a Fokker-Planck model or something, this. Okay, so what's the punchline of all this? The punchline is, especially because I'm getting close to time. Sorry, I love this stuff and nobody else is interested in it. So that's why I get all distracted. And I'll show you much more like observationally accessible stuff in a moment. The punchline for this is what happens at very small radii for very large degrees of stripping, what happens to the density, but also what happens to, for instance, the density squared, because the annihilation goes as the density squared. And this curve shows you as you lose mass, how does the integral of rho squared dv relative to its original value, how does that change? This is how the flux would go if dark matter particles were annihilating with one another, and you were detecting that in a gamma ray experiment. And what it shows you is that, you know, if you had a one-to-one decrease in flux as things got stripped, you'd be on this line, and that it's slower than that, which is kind of what we knew or suspected, that substructure is going to dominate the annihilation signal because the dense parts will survive for longer, right? So rho squared will be larger. But interestingly, exactly what the answer is depends quite sensitively on what the inner slope of the profile is, right? Okay. So that was the summary of that. I think I'm going to, in the interests of time, skip over the middle part of this quickly, and then go to the last part of this. So in the middle part, I was going to talk about this annihilation signal. This is the Fermi's map of the gamma ray sky, and I was going to talk about this boost factor. But I think, as I say, I'll skip over that a little bit. And I think instead what I want to talk about is this, because this is sort of a completely different part of parameter space. So I was saying that The central part of the halo forms out to the scale radius more or less when growth is rapid and you have major mergers. And then it kind of stops and freezes in. And then you build up this envelope around it that is a steeper density profile. So the core density you get and the scale radius you get, they kind of mark the end of this era of rapid growth. And there are simulation results on this from about 10 years ago or more from the Shanghai group that sort of map this out very nicely. Where they basically show that halos grow rapidly and then slowly. While they're growing rapidly, the scale radius and the virial radius kind of increase in sync. They keep getting mixed up. But then as growth slows down, the scale radius remains kind of constant, so the core density remains constant as the virial radius grows. And the net result is concentration is constant up to some point and then grows with time. The challenge observationally is that if you really wanted to measure that, you'd really want information about the density here, and that's neither easy to get from galaxy dynamics, which work best here, nor is it easy to get from, say, galaxy-galaxy lensing, where you want actually a bigger area, so it gives you information out here. So this work was using very long slit spectroscopy on a large number of galaxies in the Virgo cluster to try to get way out on the edges of the galaxy and really explore the dynamics there. But there are other ways of doing this. I'll show you some of those in a moment. I am not an observer, so I had a complicated, I kind of took galaxy size, some measure of galaxy size. I said, well, it's kind of the size of the galaxy in the optical. Can I call that the optical radius? And I was told, no, you can't call it the optical radius. We already have an optical radius. Anyway, there's some size I've taken, which comes from a complicated analysis of scaling relations by Nathalie Ouellette, but that's kind of galaxy size. And technically it's measured at this isophote, so I'll call it R23.5. And you can go through a lot of modeling to figure out how this should behave with mass that I'll skip. But if you put all this into a sort of little semi-analytic model where you put in scatter and so on, the prediction is that the density, the mean density of dark matter interior to the outer edge of the galaxy, where by outer edge I mean this R23.5, should be constant. Independent of galaxy mass, roughly. So here it is over 3 decades in mass, and it varies, a little bit, right, by factors of 20 or 30% maybe. There should be a trend in that older things should have higher densities. So that's kind of interesting. And if it was the 1970s, you could actually turn this into a model for galaxy formation. You could say the reason galaxies form is because they're in this area where dark matter has achieved some density and so on, right? Like it has that appeal, that kind of scaling relation, old school appeal to it. Okay, we went and checked whether those analytic models are correct in simulations. This involved a bit of complicated sort of rescaling. And I'll just sort of show you the results of that. So you go and pick subhalos in simulations. You try to figure out what galaxy would live in that subhalo. You go to the radius that galaxy would have. You measure, et cetera, et cetera. Anyway, it's a bit involved. But interestingly, we get exactly the same result pretty much in the simulations. If we go and do that adjustment, the simulations also say these should be the mean enclosed densities that galaxies have. These pink symbols are field galaxies. The rest of them are from a cluster, from a simulation of a cluster. And they're kind of hitting the low end here. The redshift, the black and dark blue curves are at redshift 0, but that's what you'd expect because these are field objects. So this all sort of hangs together. And then you can go and measure what these densities were from the mass modeling of the galaxies in this survey of Virgo. And these were derived by Nathalie Ouellette. And here they are. And to me, this is the most amazing thing, that they actually hit the diagram at all, that they're even roughly in the same place. I was not expecting this, because nobody's looked at this in this way. They've looked at it kind of object by object, but not for a whole population. And yeah, there they are, right? So you can see the average, the scatter, pretty good. Maybe some trends here in the data, right? This might be actually the too big to fail problem rearing its ugly head here, that these are all, a lot of these galaxies are dwarf ellipticals, dwarf spheroidals, and they have low densities. There are definitely complications, like if you break them up by morphology, it's not a uniform mix by morphology, so you might worry that there's systematics in the mass modeling or that different galaxies are doing different things. But the thing that really, sorry, I'm going to try to wrap this up. The thing I really wanted to do with this, because this was something that I'd wanted to know how you could get to this observationally for years, was, halos are kind of growing from the inside out. Virgo should kind of have grown from the inside out. So if you have something you think traces when a galaxy formed, that thing should be different in the middle of the cluster. So you should see a trend in the cluster. Virgo, unfortunately, is a very messy system. It's actually 3 different systems centered around 3 different bright galaxies. And then this survey didn't actually cover all of it. It covered like this bit. So that's the pattern I would expect to see, and what you see is this, right? Here, the symbols are coded by the density of dark matter in that galaxy. Okay, not the stellar density or any of the stellar ages or properties, but the density of dark matter. And you kind of see that, yeah, the dense stuff's in the middle of the cluster. And you can compare that to various other distributions, the light distribution, the X-ray distribution. You can do some statistics on it and find that I was kind of embarrassed to show this because I was showing this to Gwen and I felt like, oh, it's KS test. Sorry, I should do something more sophisticated. But anyway, you can show that the outskirts of the cluster have a different distribution of galaxy dark matter densities than the center at about 3 or 4 sigma. And what's cool is it also matches, if you go back and find other people's mass models and try to put them on these plots, it all sort of adds up. Like other people are getting the same results, but they're getting them typically 1 galaxy at a time. They're not probing a sort of whole environment. You can even go to higher redshift and start to test the redshift dependence here. And then this is the point that I was struggling to put on this. If I take constraints of the mass distribution of the Milky Way and ask where do those land on this plot, it's interesting. Not only do they land pretty much right where you would expect for the redshift 0, 10 to the 11th solar mass object, but they're tilted so much, they actually in a funny kind of way give you a bit of a constraint on the stellar mass of the Milky Way. Like if you believe this, you could get the stellar mass of the Milky Way, or if you believe the stellar mass of the Milky Way, it confirms this. You can pick whichever one you want. Anyway, so I think this is a new way of putting, these mass models and kinematic measurements on something that I can now understand. And that was a victory for me, if not for anyone else. Okay, there we go. So I'll leave you with the conclusions of this. I think we're sort of moving towards a model for mass loss that has deeper roots and can solve this problem of understanding structure formation over a very wide dynamic range. A problem I didn't talk about is there's some disagreement over what the central density of the highest redshift objects is. But at least in galaxies, observations seem to, kind of test out what you would expect the dark matter densities to be and confirm them. And that's a potential tool then for measuring when the structure, the galaxy structure assembled. Okay, so I'll stop there. Thank you.
Can you briefly summarize the central density problem?
Sure. I'll let me just go back to this. I'll try to keep it at 1 or 2 pictures, but you care about this integral, this boost factor, what rho squared dV is. That if you work out what it is for an NFW profile, it's a very steep function of concentration. So it depends sensitively on what the concentration is. And you can ask, what is the concentration right down to the smallest scale structure in the universe? Because that's what matters for the sort of calculation. And these are various concentration mass relations carried down to, well, here it's below 10 to the minus 5. So really to the smallest scales you might worry about. And This one is an analytic one by Okoli and Afshordi, which assumes it assumes conservation of energy as something formed. So it's not a very, it's a very much a theoretical model. The rest of these are based on simulations. And previously, people had said, oh, there's reasonably good agreement. The simulations are all finding the same thing. That's fine. The thing is, the simulations are not simulating this, because you couldn't possibly simulate this. Here you would have to take these tiny planet mass things and track their evolution from redshift 30 self-consistently down until they were in a 10 to the 12 solar mass halo, and no one can do that. So these values are actually, if you go in the simulations and measure concentration, you get values down here. If you assume it evolves the same way it does at low redshift, then you get this. But if you actually go and look at the densities in those early simulations, the squares here are the densities. And these are just what you would predict for different concentrations. Basically, everybody else's low redshift concentration models are the lower curves here. You need a much, much higher concentration to actually match what you see in the redshift 30 simulation. So there are kind of two solutions. One is these simulations, that density gets diluted with time. And if so, we don't know the mechanism for that. Or the other is that this is right and is conserved. If this is right and conserved, the interesting kind of implication is you can take all the limits people get from Fermi and things like that and lower them by a factor 20 or 30, at which point you basically rule out electroweak scale WIMPs completely, right? So if it's right that these tiny little first halos conserve their density, this is all over this game. It is possible they don't. But if they don't, we haven't yet found the mechanism by which that density drops. It's not there in any of the stuff about concentration, that central density drops. So the question is, does the central density drop or not, right? And it has to drop by a factor of like 6 or 8 in density, or 20 or 30 in boost factor, or more. Yeah. So that's the nature of the problem. The stripping story doesn't do it, and also we tried violent one-to-one mergers, and we were trying to see if we could get outcomes that were well below the dots here, and we couldn't, even with very violent mergers. So we haven't figured out a way to do it yet. I have a theory that three-way mergers might do it, a la sort of violent relaxation. But yeah, we haven't figured out. I mean, the problem is I'm the only person who, I haven't heard anyone else notice or care about this problem. So I have to get a couple of other people caring about it before I do follow-up work to try to investigate what's going on. Yeah. Anyway.
More questions?
Okay.
Just back to your mass loss prescription. Does softening length play a role at all when you're trying to predict, I guess, the halo's response to the mass loss?
So it does in matching the simulations. I mean, you certainly have to worry about that and about resolution overall. I mean, you're trying to sort of make a model for an artificial process, right? Like real objects are obviously going to be more complicated. Having said that, the thing we're trying to model is sort of the infinite particle, zero softening length limit. I have thought that you could add that in. You could eventually go back and, what might be interesting is to, if you had an easy way of adding that in, like modifying the potential or something, you could go back and reanalyze things like, Aquarius or Illustris or something and say, how much stuff are you missing? Like, here's a model that not only tells you what the real answer should be, but also has an adjustable parameter to correct for softening, and it tells you how big a difference there is. Yeah, yeah. I think that would be an interesting thing to do.
Great. So if there are no more questions, shut the time tapes again.
Thank you.